Yes, we are live. Yes.
Professor Datta, are you ready?
Yes, yes.
Yeah, okay. So hello everyone. Today we have Professor Jaya here to speak on abelian variety, and Professor Swarnendu Datta will chair this talk. So Datta, can you take over, please?
Yes, so it is our pleasure to welcome Professor Jaya Iyer from IMSc Chennai, and she is going to give a talk whose title is Abelian Varieties 1, and we'll be discussing the basics of abelian varieties. Professor Iyer, please, we are waiting for you to start.
So thank you very much to the organizing committee, especially Devendra has been very helpful and kind. So he has been very efficient and sharing a lot of information week after week. Yes, I'm really grateful to all the efforts all of you have been putting up over all the several months now. So actually the plan is to speak on abelian varieties in these two talks. So let me just give some overview on what I would like to discuss in these two talks. So first, actually today I would like to discuss the basic definitions and properties of abelian varieties. Then I would recall rigidity theorem and give some consequences of them. And then today mainly I would like to discuss abelian varieties over the complex numbers. And in the next talk, I would sort of give something more information on abelian varieties over other fields perhaps, and also speak on Jacobian varieties associated to some special curves and so on. But today the focus would be essentially on abelian varieties over the complex numbers. And we want to recall a very important theorem. This is called the Appell-Humbert theorem. So this is what this first talk is going to lead to actually. So I would just recall the definitions and basic notions one would require to explain, at least understand the statement of Appell-Humbert theorem. So I would want to say that I am not going to produce any proofs as such, because this is all something which is already written in many books. So a basic reference is Mumford's Abelian Varieties, which is very popular and which is very nice actually, because it deals with abelian varieties not just over complex numbers, but also over other fields and discusses endomorphisms and so on. So I think I find it very useful to look at actually, Mumford's abelian varieties. But of course, I think one would also like to look at James Mill's abelian varieties. So that is also there online. So maybe these two references would suffice, I guess, to understand the basic notions which I would like to look at actually. So this is the plan of the first talk, and in the next talk, I would maybe recall theorem of square, seesaw principle, theorem of cube, dual abelian varieties, and discuss the statement of Riemann-Roch theorem, and explain Jacobian varieties. And Devendra asked me to look at hypergeometric Jacobian varieties. So I must confess, I don't know what it is, but I think I have another 2 weeks to look up these objects in detail and try to explain it as well as I could actually. Okay, so this would be the plan. So let me go a bit slowly. So abelian varieties. So actually what is this? So as the name suggests, we are going to look at algebraic varieties. So a group variety, so this is actually an algebraic variety over a field K together with regular maps. So so you have two maps which defines a group structure on such a variety. So the first map is what we call as the multiplication map, M from V cross V over K to V. And then we also have a map which we denote by inverse. So this is from V to V here. And then actually we have a special point in the K valued points of your variety V, which we denote by E, such that the structure on V of, you take the variety over K and then look at its K bar rational points on V as also. And so you look at V K bar. So this is defined by M, your multiplication map, and the inverse map. So this forms a group. and with an identity element. Okay. So there is also a right translation map for any element which is a k-valued point of your variety V. So what is the translation map according to a k-valued point? So this is just a composition of an inclusion which is V to V cross V, and then you can compose with your multiplication map. So basically it would mean that you take a k-valued point and send it to XA. So this is the notation actually. So this is same as saying that you look at the pair X comma A, and then under the multiplication map look at XA. So a group variety, first property is that this is a non-singular variety. So that means it's a smooth variety. So how does one see that actually? Because generally if we just talk about a variety, it can have several singularities actually. There could be a singular locus of any dimension as such. But whenever you have such special maps defined and a multiplication and an inverse, so that there is a group structure actually, if you look at the algebraic points in the algebraic closure, so then actually we say that it's going to be a non-singular. So that means each point is a smooth point. So why is that? Because the first thing we notice is that the translation maps, so they are actually isomorphisms of varieties. So actually generically there is always a k bar, so there is going to be a smooth point. And now actually you can translate a smooth point to any other point on your variety. And that will prove that any other point is also a smooth point. And it suffices to check the non-singularity over the closure, and that implies that the variety you start with is non-singular over the base field itself. Okay, so this is a nice property of group varieties, that it's a smooth variety. And now actually if you consider a complete connected group variety, so we want it to be a complete. So that means in the case of abelian varieties over complex numbers, it just means you are going to look at compact varieties. So such a compact connected group variety is called an abelian variety. And they are projective and commutative. So we would just look at the next slide where we say that, where we try to indicate why they are going to be projective and commutative.
There's a
So
question in the chat.
chat box.
Yeah, regular map are polynomial in local charts.
Right. Regular map, because algebraic varieties, they are defined by polynomial maps. That's correct.
Okay.
Algebraic set, so that's how it's going to be. Regular maps, yes, sure. I should answer that, yes. Okay. So I must say that I am not looking at chat box immediately.
That's okay. We will inform you maybe.
Okay, yeah. Okay, maybe I'll keep it in front of me, yeah, so that I can look at it. Okay, so this is what we get actually. So you get a complete group variety. It's called an abelian variety. So now let us look at some properties. Like, okay, we have just defined group variety, and then we want to say, basically obtain these two corollaries, that the group law on an abelian variety is always commutative. Okay, and then we want to say that any regular map between two such abelian varieties is the composition of a homomorphism with a translation. So basically you start with any regular map between two abelian varieties. It is going to be, actually it will respect your group laws up to a translation. So this is another way of saying this statement. And why is that actually? Because a priori actually we have just defined some multiplication map and an inverse map. And then we have said that, okay, this forms a, or algebraic closure, you get a group structure and so on. But then actually we say that, okay, but a regular map, actually there is no, if you just take two varieties and then you are going to look at regular map, so that means it is defined by polynomial equations and so on. So there is no way, I mean, there is no reason why one would expect the group laws to be preserved by them. That means it should be a group homomorphism. But this is indeed true actually. And the proof essentially follows from rigidity theorem. So the rigidity theorem basically says that if you start with a regular map from F from V cross W to U, where we assume that V is complete and the product, that is the domain of your map, V cross W is geometrically irreducible, then, and if you have 2 points, k valued points, say U and V on V and W, and the W, little w which is a k valued point of W, so that F takes an axis, if you like to call it V cross W, and the other axis V cross W, little v cross W. So both the two axes are collapsed to the same point, U, little u. So then we say that the theorem says that then the whole variety itself collapses to that point. Right? So this is sort of a strong statement actually, because you are just saying that two coordinates, coordinate axes for this product variety, they are collapsed to a fixed point which we denote by little u, and the whole variety itself becomes a constant map and takes the value little u there. Right? So from here, actually these two corollaries can be obtained, that any regular map between two abelian varieties, actually this is actually a group homomorphism up to a translation map. And the way one likes to look at it here is that the proof essentially says use rigidity theorem, and to prove something is a homomorphism, we have to say use the multiplication map and say that you take some two elements x plus y, so that is you are going to use a multiplication map composed with f, and that commutes with f composed with the multiplication map. So something, take the difference, and one checks that to prove something is a group homomorphism, one would like to say that f of a plus w equal to f of a plus f of b. So where plus in this case is the plus operation in b. So if we say that this is not a homomorphism, so look at the difference. So that means f of a plus b. So that means f composed with your multiplication map. So this is, and take the difference with the multiplication map composed with f here. So take that difference, and one checks that such a difference map, it collapses the two axes, and that implies that they are going to be identically same, and that will prove that it is a homomorphism. So that is the basic idea of this corollary. Okay, how one proves that. And the next case is that the group law on an abelian variety is always commutative. So this again uses rigidity theorem. And if we say that here what one considers is that you look at the inverse map, and by the previous corollary, so the inverse map is going to be a group homomorphism. So once it is a group homomorphism, because one again checks that your inverse map, actually if it is yeah, so it's a group homomorphism, so that basically implies that your group law is going to be a commutative action. Okay, so this is what, so these are two nice corollaries and nice statements you get just from your basic definitions which you can define over such group variety, which is assumed to be complete as well. So rigidity theorem is very useful and to prove such statements. Okay, so now actually from now on, I would like to look at abelian varieties over complex numbers and try to explain actually how some nice properties of abelian varieties and line bundles on them. Okay, so the way we have defined an abelian variety, it is defined over any field. So in particular, you can look at abelian varieties, say of dimension G over complex numbers. So we want to have some kind of a structure of your on your abelian variety, in the sense that we want to understand that if it's an abelian variety, so by the previous two slides, we know that it is a non-singular So that means it's a smooth variety, smooth and complete. So smooth and complete basically means that it's a compact complex manifold, right? So it is a compact complex manifold. So we want to understand the topological structure of such a compact complex manifold. And the first consequence of the variety having a group structure basically means that it is a compact connected complex Lie group, because a Lie group basically means that you have a group structure on it. So in this situation, we want to understand the topological structure of your abelian variety. So for that purpose, so whenever you have a Lie group, so you can, so there is some in Lie theory, so there is going to be an exponential map which is defined on the tangent space of your Lie group, and you can look at the identity element of that. So you can look at this tangent space to your Lie group at identity, and then there is a map to the Lie group, which in this situation is A, which are with C valued points. So this exponential map, so this is actually a map of complex manifolds. And in this situation, because your tangent space also has a group structure and your abelian variety, so this again by definition has a group structure. So this is in fact a homomorphism between two groups actually, which are also manifolds. And in this situation, so this map is all denoted by the exponential map, which is just taking a vector z to exponential of z comma v here, right? So this is what you get. So I think so. So this is what you get, and but the basic fact here is that the exponential map is surjective, and its kernel is going to be a full lattice in the complex vector space, which is the tangent space here. So a lattice is precisely a maximal discrete subgroup of your complex vector space. Say for example, because I think by now all of you have looked at elliptic curves. So in particular, if you look at elliptic curves over complex numbers, so we must, all of us have seen that this is just C modulo a lattice. That is a discrete subgroup generated by two elements, which are your complex numbers, right? So this is C modulo a lattice, and any elliptic curve topologically just looks like that. So abelian varieties over complex numbers, you can easily see from here that this is a generalization of elliptic curves, because elliptic curves are one-dimensional abelian varieties. And now if you are going to look at higher dimensional analog of elliptic curves, so this is topologically just going to look like C power G modulo a lattice. So just in analogy with the elliptic curves, so actually where G is 1, so we can look at C power G modulo a lattice. So a lattice in this situation will have 2G number of generators, because for elliptic curves you have only 2 generators, but for when G is bigger than 1, so you have 2G number of generators, and that's a maximal discrete subgroup in your complex G dimensional vector space, right? So this is the topological structure or the manifold structure on your abelian varieties over complex numbers. And what is this CG? So CG you can recognize as a tangent space to your abelian varieties at your identity element 0. So this is how your CG can be recognized, and this L can be recognized as the fundamental group of your complex abelian variety. Okay, so this is so even though we have written this to be equal to CG modulo lattice.
Can you repeat the last argument? CL is fundamental group of.
So L is the fundamental group of your abelian variety. So this is basically because if you you are going to look at the universal covering of your AC. So this is going to be just a CG, because in this case, so you are getting the vector space, which is the tangent space actually. So which has two-way fundamental group. So that's the universal cover, and then you have so L basically becomes the fundamental group of your abelian variety.
Okay.
Because it's a quotient of CG. Okay, so this is the topological structure of your abelian variety. So this is another way to look at complex abelian varieties. That you have a universal cover and you're going modulo this discrete subgroup, which is an abelian subgroup. Okay, so these are some nice facts of abelian varieties over any dimension, because G can be anything here. And so you start with some group variety over complex numbers, which is connected and compact. So one immediately gets this structure that it is actually up to homomorphism, or not homomorphism. In fact, as manifolds, as isomorphisms of manifold, complex manifolds, it is CG modulo a lattice. So we can ask the converse question. Suppose you start with a lattice like this, NL, and a complex torus, which is CG modulo some lattice. So is that an abelian variety? So that means, does it have a variety structure, right? So, and the point here is that that is not true actually whenever G is at least 2. Actually, so this is the main difference between elliptic curves and abelian varieties in higher dimensions. Because if you look at elliptic curves, so you're just going to look at C modulo a lattice. So any such complex torus in dimension 1, so that has a variety structure, because that can be embedded inside P2 via your Weierstrass forms, right? And then one knows that the Weierstrass and 1P and P prime, that actually gives an embedding of a complex torus inside projective space P2, and that defines a variety structure on your elliptic curve. But now actually if you start with a lattice like a complex torus, which is CG modulo a lattice, where G is bigger than 1, strictly bigger than 1, then there are no such natural embeddings inside projective space, even though this is going to be, because L is maximal discrete subgroup, ensures that your quotient is going to be a compact manifold once it is maximal discrete subgroup. But then you don't have such natural, some canonical set of regular maps, which defines an embedding into some higher dimensional projective space. And that's why this is, one has counter examples for such complex torus which do not embed inside projective space. So that brings rise to the question, when does complex tori embed inside projective spaces? Right? So that's the next question one can ask actually. Because if you look at the moduli space of complex torus, so this is just saying that you fix one complex vector space G, and you can have several such lattices, maximal lattices L, and then they would give rise to different complex tori. And when such a complex tori gets embedded in some projective space, so that it obtains a variety structure. So that's the next question we want to address. So can we characterize such complex tori, right? Okay, so to understand that, so that is precisely given by Appell-Humbert. Any questions so far? Okay, so topologically, or as a real manifold, the complex torus CG modulo a lattice, this you can identify with R mod Z and take 2 copies of that actually. So why is that? Because your CG, you can write it as R power 2G, right? And then you have L, which is basically, as I said, it is maximal discrete subgroup of CG. So a maximal discrete subgroup has 2G number of generators. So topologically, you can recognize this as R mod Z and take 2 copies of them. But R mod Z is just your circle S1, your unit circle. And so you get 2G copies of S1. So topologically, so we have obtained a topological structure of your complex torus. So these isomorphisms which I have written, so this is only as real manifolds, because we don't define a complex structure on S1 here. So this is only a identification as real manifolds. So, but this identification helps us to compute the cohomology groups of your complex torus, because in any case your cohomology is determined only up to its topological structure. So we don't care about the complex structure to define, to make computations on cohomology. So we are at liberty to make such identifications. So you look at, so why is this useful? Because now actually the cohomology of circle is something which all of us know. And so because it's a one-dimensional real manifold, so it has only the zeroth cohomology and the first cohomology. So the higher cohomologies are 0. So what is the zeroth cohomology of S1? So this is just 0 because it's connected. And then if you look at the first cohomology of your circle, so this is just generated by the loop here. So this is again Z here. And now actually if you look at two copies of S1, say S1 cross S1, so then we can apply Kunet formula and obtain that the zeroth cohomology is Z. And then if you look at the first cohomology, so this is going to be two copies of Z, because S1 cross S1 is just your torus. So that is your elliptic curve, the topological structure of elliptic curve. And so actually you have two loops which determine the first cohomology of S1 cross S1. And then H2 is dual to H0. So that is again Z. And it's two-dimensional real manifold. So the higher cohomologies are 0. And similarly, you can iterate this process. So that means you apply Kunet formula further, and then you can check that if you look at the cohomology groups of product of three copies of S1. So this is basically Z, Z cube, and three copies of Z and Z, and so on. And for 4 copies of S1, product of 4 copies, so you have such cohomologies of these groups. And actually, if you want to do it further, so actually you would get a what one calls as Pascal's triangle. One can check that. So basically, one would obtain that the dimension of the Rth cohomology of 2G copies of S1. So this is basically 2G choose R. Okay. So this is how one can understand the cohomology groups of your complex torus CG modulo a lattice. And now actually one can ask actually, so you have your cohomology groups. So here we have just said that, okay, you are just looking at so many copies of Z and so on. But we want to understand, is there further, what is the, what if you can have some further structure on your cohomology ring of your complex torus. So actually one has very nice result in this direction. So you have canonical isomorphisms from your Rth cohomology of your complex torus with the exterior power of H1. That means the first cohomology. So what this says here, so the first isomorphism says basically that your cohomology of your complex torus is basically determined only by its first cohomology. Right? So there is nothing new occurring in the higher cohomology. So that means you are just going to look at exterior powers of your first cohomology, and so that determines the whole cohomology ring of your complex torus. And what is the next isomorphism? Here you get. So the next isomorphism says that the Rth cohomology, it is something very much related to linear algebra. So that means this Rth cohomology, it has a structure of the group of multilinear forms which are alternating. So that means these are the alternating R forms on your lattice with values in Z. So this one can say as the Z valued alternating forms on your lattice. So this is something very discrete in the sense that we are just going to look at the lattices, which is a discrete subgroup, and we are going to look at alternating forms which come from multilinear forms on your group L here. So the cohomology has very nice identification in the case of complex torus. So this is something we want to remember, and this actually helps in several other properties in understanding line bundles, polarizations, and whatever one wants to understand on complex abelian varieties. And something, so this is something very unique to abelian varieties actually. So such identifications actually you don't normally find in other kinds of varieties. And so actually people like to understand Hodge conjecture on abelian varieties, especially special abelian varieties and so on. So that basically sort of uses the structure of your cohomology of which is identified with the exterior powers of your first cohomology and so on. And one normally tries to look at the group of Hodge classes sitting here. We also try to understand, identify it with some exterior powers of the codimension one objects here, divisor classes. So such identification is very unique to abelian varieties, and so they are useful to prove many other theorems, understand other structures. Okay, so once we have said that the cohomology and all, it is sort of, you have made some identification with alternating R forms and so on. So it basically says that, okay, now there is some linear algebra which is going to happen actually. So once you have alternating forms and all, so, and we are working over complex numbers, so some kind of Hermitian forms and alternating skew forms and so on, everything is going to show up actually. And so let me just recall what all this is. So just keep in mind that we want to understand which complex tori embed inside projective spaces whenever your dimension is bigger than 1. Because when dimension is 1, we have already seen that any such complex torus in dimension 1 gets embedded inside P2, and that gives an algebraic structure, and so it is actually an elliptic curve. But if you are going to look at higher dimensional complex tori, we want to understand embeddings, and embeddings are basically given by ample line bundles, and so we want to understand ample line bundles on such complex tori. Okay. Okay. So to understand ample line bundles, so what we want to understand is the first Chern class of ample line bundle. So a first Chern class of an ample line bundle is actually going to lie in H upper 2 of a complex tori with values in Z. So the first Chern class is going to be H in H2 CG modulo lattice Z here. So such a Chern class of ample line bundle, so it corresponds to an so here in this case R equals to 2. So basically it means that your first Chern class can be thought of or can be identified with an alternating 2 form on your lattice with values in Z. So the question is that if you want to understand if such Chern classes exist, so we have to start looking at alternating 2 forms and characterize which ones actually correspond to your first Chern class. That means we have to put some conditions on this group of all alternating 2 forms, give some kind of conditions in this set here, and which actually comes from a ample line bundle. So that means we have to look at some special alternating 2 forms which possibly are the first Chern class of ample line bundles. So that brings rise to putting some conditions on alternating 2 forms on your lattice with values in Z. Okay, so that's how one can try to understand the next couple of slides. So we'll start to look at such alternating 2 forms which come from line bundles. So we start by looking at more generally at Hermitian forms on your G-dimensional vector space, and the real valued skew symmetric forms on CG, satisfying the identity that E of V comma IW is same as E evaluated on your elements V comma W. So this is something I'm just going through fast. So basically what I'm trying to say here is that, so there is a one-to-one correspondence between Hermitian forms and skew-symmetric forms. That means alternating two forms on your lattices. So you start with some skew-symmetric form, that is same as your alternating two form on your lattice with values in Z. And now you can extend it to skew-symmetric bilinear form, which is R value. So given such a E, you can cook up a Hermitian form. So this is what this statement says here. So given such a E, you can obtain a Hermitian form having such a property. So that the imaginary part of your Hermitian form is basically the alternating form you start with. And conversely, you start with the Hermitian form, you split up into its real part and its imaginary part, and then take its imaginary part, and you can, that would correspond to a alternating two form. Okay, so you have a one-to-one correspondence between alternating two forms which are real value together with Hermitian forms on your complex space. So once you have that, so what is a what is something special about your alternating two forms which come from which arise as first Chern class of line bundles is basically that such alternating two forms, they take your lattice L cross L inside cell Z. So that means it is Z value. So this is something very special about the alternating two forms associated to ample line bundles. So this is the statement which characterizes ample line bundles. And then we say that the Hermitian form is positive definite. So these two conditions say determine the ampleness, or that means say that your line bundle which provides an embedding inside projective space is going to be ample line bundle. That your corresponding first Chern class, which then one can cook up a Hermitian form. So then that becomes positive definite, or in other words, is non-degenerate. So basically we look at this complex torus. We say that this is polarizable if it admits a Riemann form. Right? So such a form, so that means such a Hermitian form is said to be a Riemann form whenever the two conditions A and B are fulfilled. So polarizable is basically saying that the complex torus, it can be embedded inside projective space. So that's all it means. So polarizable basically means that there is an ample line bundle on this complex torus which embeds two sections, global sections, embeds it in a projective space. And so such a polarization exists if and only if you can have a alternating two form on your lattice L fulfilling conditions A and B. Okay, I hope this is clear now, the statement. So a polarization on the complex torus implies that it has an ample line bundle, and hence it is, then its global sections or a power of them will embed it in a projective space. And once it is embedded in a projective space, then your complex torus is a projective variety, and then we call it as an abelian variety, because a complex torus a priori has a group structure and it's embedded inside projective variety, inside a projective space, so it becomes a projective group variety. So in particular it is complete and compact, and so it becomes an abelian variety. Okay, so a complex torus is of the form A bracket C if and only if it is polarizable. Okay, so this is the content of your first theorem which we have sort of discussed. So now let us look at line bundles, because polarization basically means that it has an ample line bundle. So this gives rise to Appell-Humbert theorem. So this is quite popular, that means it is quite famous, because it sort of because as we have seen, your abelian varieties or complex numbers, topologically it is just S1 and taken are 2G copies of that. And so we also want to understand line bundles on complex abelian varieties, and it turns out that line bundles on Abelian varieties also have a very nice characterization. So basically we have seen that we need to deal with lattices and so on. So it says that there is up to linear algebra, it is determined only by a Hermitian form, a non-degenerate Hermitian form, and a semi-character on the lattice. So this is what an ample line bundle is determined by. So let us just try to see what it means. So the Appell-Humbert theorem, so it says that any line bundle is determined by a pair E comma alpha, where E is an skew symmetric form, or you can also call it as an alternating two form on your lattice as before, and this alpha is a semi-character on the lattice with values in the circle. Okay. So that's all. So semi-character means that it is not exactly a character. That means it's a group map, but there is some factor which shows up. And so that's why it's called as a semi-character. So a line bundle is determined by only this linear algebra data. So this is also something very unique to Abelian varieties. So this is something not happening on any other varieties in algebraic geometry. Okay, so let us try to understand how a line bundle corresponds to such a pair, that is a Hermitian form together with a semi-character. So a line bundle, how do we look at it? So a line bundle is essentially an element of the Picard group of A. So how is this obtained? So you have to look at the exponential sequence. So this is the exponential sequence, which is very famous in algebraic geometry, quite basic also. And so the map from O to O star is basically you start with the holomorphic function on A locally, and then you can look at its exponential. So you raise it f here, and so this is the map here, a sheaf map. So this is a local definition. And now corresponding to any sheaf sequence, so you can associate the corresponding sheaf cohomology sequence. So you have a sequence which is H1AZ to H1AOA to H1 of O star. And then you would come to the second degree terms, H2A with coefficients in Z and so on. So a line bundle is essentially an element, that means a class in H1A O star, right? And so that is basically your Picard group of A, that's the definition. And pick zero is going to be all line bundles here whose first Chern class is 0. That means it's correspond under this homology sequence, its class is 0. So this is same as saying that your line bundle comes from H1AOA modulo H1AZ. So that group is denoted by pick 0. So that means all those line bundles whose first Chern class is 0. Okay. So what we have seen now is that you start with a line bundle in H1 O star, and then you look at its image in H2AZ. So this is going to be your first Chern class. But now we have seen that topologically that your second cohomology group with coefficients in Z is identified with alternating two forms on your lattice with values in Z. So that is going to be your alternating form psi. Let us corresponding to L, let us denote the alternating form by psi. So this image form is a Riemann form. Just a moment. So this is something very unique actually. I mean, you start with something, a line bundle, and then the image in this group is going to be a Riemann form. So that means if this psi you think of as an alternating two form on your lattice and so on, then one can see that it fulfills the two conditions which we required here, that the bilinear form has to satisfy, fulfill A and B. So, I mean, B is fulfilled whenever L is ample, but otherwise, even for any line bundle, even if it is not ample, at least the first condition will be fulfilled. So the image form is a Riemann form. And now what is a semi-character? So semi-character is actually a map of two groups. So which is L is a group, and then U1R is basically the unit circle. So that means you look at all the complex points with modulus 1. That is the unit circle. So this is actually a group homomorphism up to this factor, which is e power pi I and image of psi lambda 1 lambda 2. So there is some factor which shows up, which if you suppress, then it actually is a group homomorphism. So that's because this factor shows up. That's why this is only called as a semi-character and not a character. Okay, so this is called as a semi-character. So the Appell-Humbert theorem basically says that you look at an exact sequence of pairs psi comma alpha. That means alpha is a yeah, so this is the first row is actually just linear algebra, right? This is something because you are just going to look at psi is an alternating two form, and then you are going to look at alpha is just going to be a semi-character. And psi you can also ask that it fulfills your condition A actually. So this is the set of all such pairs psi and alpha. And now the projection is that you forget your alpha and psi goes to this set of all Riemann forms. And the kernel is basically going to be alpha. And this is your home L in U1R. So I have not really defined the group structure on the pairs psi comma alpha. So this is, I've just loosely written this. So essentially this is the set of all such pairs. And then we have to, so there one can define a group structure on it also actually. And on that set. So you can have that first row. And what it says is that this is a standard sequence which we just looked at, pick 0 to pick A to the kernel. So this comes from your sheaf sequence. So the sequence which we have written here. So this one actually you can actually obtain from that. You can obtain this second row here. So that means the Picard group, that is the set of all group of all line bundles on A. So then this map, right arrow is basically looking at its first Chern class, and then the kernel is going to be to precisely pick 0. So that means all those line bundles whose first Chern class is 0. So basically Appell-Humbert theorem says that the first exact sequence is actually isomorphic to the second exact sequence. So this is very interesting because your first exact sequence, it is just cooked up from linear algebra on your lattice. And the second one comes from geometry because you're going to define it via some sheaf exponential sequence and so on. So this is very interesting and very deep. And so the Appell-Humbert theorem says that your Picard group is basically identified with pairs, which is psi, which is alternating two form, satisfying the Riemann bilinear properties, and a semi-character. Okay, so this is what I want to discuss, what I wanted to explain actually. And so perhaps next time I would go further and explain some more things which would perhaps be useful in the next talks by other people. So any questions? Actually, I'm happy to take.
Thanks, Professor Jaya, for a wonderful talk. I have some questions.
Yeah, sure.
But waiting for other people, maybe they have first, then I will ask.
Are there any questions from the audience?
So I have this question that this theory of elliptic curves and modular forms and modular curves start with certain problems in integration and periods of them, like there's some Legendre differential equation of first kind and second kind,
Right.
which are special hypergeometric functions.
Mhm.
But when we try to study the general hypergeometric equation and its solution,
Mhm.
then how theory will evolve, right? So in the classical case of Legendre equations, and then we come to the Weierstrass forms and that kind of elliptic curves and that whole rich theory.
Right.
But if we try to replace some other differential equation and try to study their function, their monodromy, and the periods generated, lattices generated by the periods arising from that equation. That is perhaps I was thinking about the hypergeometric Abelian variety.
Hmm.
So is it easy to see for you to?
Yeah, that should be addressed in my second talk actually. So
Yeah, so that is what. So this is these generators in the lattices come from some integration problems, right?
lattice is actually no. This is um, see actually in algebraic geometry we find abelian varieties coming in different contexts, and so one is like Jacobian of curves. So actually, as you said, maybe you can look at special curves in projective spaces, which come from different satisfying certain properties and so on. So some equations you get and so on. And I suppose that would define certain curves in P2 and equations in say P2. And then you can look at its Jacobians. So that would be something higher dimensional analog of elliptic curves.
Okay.
And, so that would isn't so Jacobians are very special abelian varieties. Not all abelian varieties are
Jacobian of something?
right. So that means you if you look at
Is
the
there any condition on Abelian variety to be a Jacobian?
yeah, of course. So for example, if you look at the moduli space of curves,
Hmm.
so that is of dimension 3g minus 3.
Yeah.
If you look at the moduli space of abelian varieties of say dimension g, which are polarization, say principally polarized, so that is of dimension g times g plus 1 over 2. Okay,
I see.
right. So whenever I think your genus is bigger than 3, or even yeah, bigger than 3, then actually your moduli space is actually a smaller, uh, it has smaller dimension than your moduli of abelian variety. So there is a what we call as a Torelli map from your moduli space of curves to moduli space of principally polarized abelian varieties. So just take a curve and associate its Jacobian. And this is actually up to some 2 cover, it's actually an isomorphism. And so this basically means that if you look at the moduli space of abelian varieties, the dimension, so the loci which parameterizes Jacobians is much smaller than the dimension of your ambient moduli space of abelian varieties. So most of the abelian varieties, whenever your G is bigger, dimension is bigger than 3, they are never going to be Jacobians.
I see.
Right. So the because of dimension reasons, most of them is going to be not Jacobians. So that brings rise to okay, if they are not Jacobians, so what are they associated to some covering to curves in some sense? So that has been what we call the Schottky problem. And so can you characterize abelian varieties and so on in the moduli space of principally polarized? Are they associated to some curves and so on? So in that context, one looks at the prim varieties associated to curves, and then what one calls as prim Turin varieties associated to curves and so on. And one says that, okay, even though an abelian variety is not actually a Jacobian of a variety, but still it is what we call as a prim-Purin variety for some very high genus curve.
I
So,
see.
right.
So this Schottky, what is Schottky problem, you said?
Right.
Okay. So there are certain Schottky groups in the realm of Kleinian groups.
Yeah.
They related with,
I don't
they
think.
correspond to the compact Riemann surfaces.
Right, but I don't think so. I think Schottky problem basically says that on your moduli space of Abelian varieties, principally polarized, are there some equations we can define which determine your more loci of Jacobian varieties? That's
I see. Okay.
Yeah, so but that's interesting. So I'll just try to look up into what you would like me to look at, hypergeometric something. So I had
Yeah, so I was just thinking about, so because this is important, so I was just thinking what kind of problem we will face when we move from this Legendre differential equation to more general hypergeometric equation and their solution, monodromy and periods to construct this variety and study them in a manner that we do for the elliptic curves.
then.
So they say that the quotient of these triangle groups are the moduli space of these varieties.
Okay.
Yeah.
Yeah.
Okay, anyway, I have just this question, this curiosity.
Oh, you are actually
Okay,
starting.
thanks.
I'll prepare it for the next talk.
It's okay.
So maybe.
Thanks.
Sure.
Are there any other questions from the audience?
So the next talk is on 8th, I guess, right?
Yeah. Thanks.
Okay, so if there are no more questions, then let us thank the speaker, Professor Iyer, for a wonderful lecture. And she'll be giving another lecture, a continuation on the same topic of Abelian varieties. And
Thanks to you, Professor Datta, also for chairing this talk. And thanks, Professor
you are
Iyer.
welcome.
Okay, thank you.
Okay, then, Ganesh, maybe you can stop the recording and live stream.
So shall I leave?
Yeah, thanks, ma'am.
Okay, thank you.
Okay, Professor Datta, you can also